In the remainder of this lecture, I want to work through this flowchart that we've just been discussing for one specific simple problem. So here we're going to be thinking of a multivariate Gaussian, a Gaussian in d dimensions. And so with speaking in terms of the 4 blocks from the previous slide, I won't this language won't be used in the remainder of the course, but for this specific lecture, I'll focus on what are the different blocks in this flowchart. With block 1 being the data, we assume that we have data points x1 through xn. We have n observations, and each observation is a d-dimensional vector that can take any value. So this is the data that we're dealing with. There's no other data that we have that we would want to model. We have a data set of n d-dimensional vectors, and we want to model those vectors. We believe those vectors can take any value. Block 2 then is the model that we want to define. So we have this data. Now what do we want to do with it? How do we want to model it, I should say. So for this problem, what we're going to think of, and I'll return to these in more detail in the rest of the lecture, we're going to say that we're going to model this data with a Gaussian distribution, a multivariate Gaussian probability distribution, and we're going to say that the n data points are i.i.d, independent and identically distributed according to this distribution. So we'll return to that in a few moments. But that's block 2. We've now defined a model for the data. We've said this is the structure that we want to learn from the data. Because this is a probability distribution, so we're looking at this problem probabilistically, we now get to add the intuition that we're saying this is how the data was generated. We have a probability model that's saying the data was generated in this way. Okay, so we have the data. We've defined the model for the data. Now we have to transition to block 3 and learn the parameters of the model. So a Gaussian has parameters. We'll discuss it. It's on this slide. We have the data that we say came from this Gaussian. How do we now fix or tune the parameters to this Gaussian in a way to explain the data? And so this is going to lead to a problem of having to define some sort of an objective function and then defining a way for optimizing that objective function. And so what we'll discuss in the rest of this lecture is something called maximum likelihood. In block 4, we can leave undefined for now. We don't need to say what we want to do with this data. We don't need to say why it is that we want to learn a model for the data. It could simply be that we just want to reduce the data so that we can have a compact representation of it and then throw the data away. Or many other reasons, several of which we'll discuss in future lectures. Okay, so looking at block 2, we're going to define a multivariate Gaussian distribution. So to refresh our memories, when we define a probability distribution, we're saying that the probability of x, or the density of x, given parameters mu and sigma, is equal to some function. That function has to be non-negative everywhere. So it's a function of x as well as mu and sigma. It has to be non-negative everywhere, and it has to integrate to 1. And the multivariate Gaussian has this specific form where we take the input vector, so this is a d-dimensional vector, we subtract off its mean, we perform this quadratic function using a mean vector mu that's d-dimensional, and a d by d matrix sigma that's positive definite. We evaluate this function, and that gives us a density for a particular point x using a Gaussian with mean mu and covariance sigma. So we get something that looks like this. If d is 2, so we have a 2-dimensional vector x, we are evaluating this function p in a 2-dimensional space. This third dimension is then the value of the function at a particular location. So we would assume, looking at this function, that the mean is somewhere, say, around 0, 0, and the covariance defines this sort of a shape. So a point in this region will have very tiny density, very small density, so we won't expect to see much data in this region, whereas in this hump region, we have large density, meaning most of the data is going to come from this region. And we remember with a multivariate Gaussian that the mean parameter defines the expectation, so the expectation of x is equal to mu, and the covariance is equal to the spread of the distribution in the various dimensions, as well as the correlation between those dimensions. And so that's equal to this function, where we take the mean of x, subtract it off a point, and then evaluate the expectation of this outer product. That's equal to sigma.